in fact all life on Earth, are only here by chance. 99% of all the species that ever lived have been wiped out in a series of catastrophes. Disasters that changed the course of evolution. 650 million years ago, the Earth froze. It pushed life to the verge of extinction. But if this disaster hadn't happened, then life today would be little more than microscopic slime. This is the story of Snowball Earth. It's almost impossible to comprehend the immense timescale of our planet's lifetime. So imagine the whole of Earth's history compressed into a single day. At midnight on our clock, 4.5 billion years ago, the planet was born. Minutes later, the protoplanet Theia smashed into the infant Earth. And our moon was formed. At 4 a.m., the first primitive life appeared. By 8 a.m., the continents were surrounded by shallow seas, full of simple bacteria. Over the next 3 billion years, bacteria colonized the oceans. Then, at 8:27 p.m., 650 million years ago, disaster struck. The planet froze. Temperatures plummeted many degrees below freezing. Ice spread down from the poles and crept towards the equator. Eventually, the entire planet was locked in a straitjacket of ice. A snowball Earth. Life had only just got started. Now it seemed doomed. Earth remained icebound for 25 million years before it finally thawed. Some microorganisms did survive and made the biggest evolutionary leap forward in the history of the planet. The catastrophe almost wiped out life on Earth, but instead kick-started evolution, creating life as we know it, including us. How did all of this happen? And how on earth did scientists figure it out? There are no traces of the ancient ice sheets left. They're long gone. But there are still clues that can tell us about this dramatic ancient ice age. The evidence is hidden away in some of the world's most remote places. These are the Flinders Ranges in the Australian outback. Today, it's one of the hottest and driest places on Earth. So it's ironic that this is where geologist Jim Gehling is searching for evidence of the coldest period in history. The area is so vast, the best way to investigate is from the air. There's a disaster story written in these layers of rock. You just have to know how to read it.
It's really like looking at a book made of rock. Every single layer has a secret on it. We look at these rocks as though they're a history book.
The spotter has located an unusual rock formation in a dried-up creek bed. It's the evidence Gehling has been looking for. A 650 million-year-old rock called a dropstone.
A dropstone is an exotic piece of rock. They shouldn't be mixed in with mud and sand. They should be together in boulder beds or gravel beds. But there they sit.
The rock may look insignificant, but it's a major clue to the powerful forces that created the frozen world of Snowball Earth.
This rock shouldn't be here. It's sitting in a rock composed of mud, silt, sand, and gravel. And normally that's impossible.
The dropstone has been transported here from thousands of miles away. There's only one force that can carry rocks like this around the globe, and that is ice. There's not a lot of ice in Australia today. So to investigate how ice could have moved rocks around the world in the ancient past, glaciologist Shad O'Neill scales the sheer walls of the Matanuska Glacier in Alaska. It's the closest we can get to our distant icy past. It's much smaller than the ancient glaciers, but it still operates in the same way.
We're taking a look at the rocks that are being transported down the valley by the glacier. And to do that, we need to go down there.
Glaciers are nature's bulldozers. They smash everything in their path. They gouge stones and rocks from high up in the mountains and carry them down the valley.
Rocks as big as buses can be transported for miles across the landscape by a glacier. I mean, the longest glaciers are hundreds, if not thousands of kilometers long, so you can move rocks over long distances.
When the ice melts, it deposits debris at the base of the glacier. This glacier is only a few hundred feet thick, but it can still carry thousands of tons of rock.
The glacier brought all this stuff down from the mountains, and when the glacier melts away, it ends up looking like a building site that's been bulldozed.
It's exactly the same process that transported dropstones to the Flinders Ranges. But there's one important distinction. The Matanuska Glacier transports rocks over 24 miles. The glaciers of 650 million years ago carried them for many thousands of miles.
Here's a great example of a rock that was picked up by the glacier, carried down valley, and then deposited. Very similar to what you'd find in Australia, where glaciers used to be in the past.
The Flinders Ranges dropstones show that Australia was once covered in ice. But they don't prove that the whole world was frozen over, because the continents were not always where they are today. The Earth's surface is in constant, very slow motion, and it pushes the continents around the planet. So where were they 650 million years ago? And where was Australia? Perhaps it was closer to the South Pole, and the dropstones came from Antarctic glaciers. The answer to that question comes from another brutal desert. Death Valley in the American Southwest. Geologist Joe Kirschvink coined the term Snowball Earth. He's been gathering evidence to prove it actually happened for the past 2 decades.
Death Valley has a series of rocks that are extremely important for understanding Earth history. It's a treasure chest.
Like the Flinders Ranges, it's not the kind of place you'd expect to find evidence of ice. Yet scattered among the sediments of an ancient seabed are more glacial dropstones.
Every time I come here, I see new things. There are those big boulders, and I see one at the bottom, and they're all dropstones. You can see that they're coming in from the top. This is one of the best places in the world to see this type of geology.
The dropstones Kirschvink has discovered here date back to the same period as those found in the outback. 650 million years ago, 2 of the hottest places on the planet today, Death Valley and the Australian outback, were covered in ice. And what's more, Grmsvtn can tell where these two deserts were at the time of the Big Freeze. The answer is in the rocks themselves. Every rock has a unique magnetic signature that enables scientists to zero in on their point of origin with great accuracy. To study this signal, Grmsvtn drills cores from the rocks containing the drop stones and measures their magnetic field.
The Earth's magnetic field is formed by electric currents flowing in the middle of the planet. The pattern of that field allows us to measure the latitude that a rock forms at.
Once they know the latitude at which a rock formed, scientists can figure out where on the planet it came from. When a glacier dumped these drop stones here, Death Valley was inside the tropics. Rock cores from drop stones in the Australian outback had an even more stunning tale to tell.
A group started studying the magnetism in the Flinders Ranges, and they thought they had a very stable magnetization. That they said, well, wait a minute, something might be relevant there.
The rock's magnetic signal revealed that 650 million years ago, Australia had been in a completely different place than it is today. When the planet was in the grip of the Big Freeze, Australia was near the equator. Here was the proof the scientists were looking for. 650 million years ago, the planet was shutting down. Life on Earth seemed destined for total extinction. Somehow, something had plunged the whole planet into a catastrophic deep freeze. The question was what? 8:27 p.m. on our 24-hour clock, representing the history of the Earth. 650 million years ago, the planet faced climate catastrophe, a global deep freeze. But what made it happen? Snowball Earth wasn't the first time the planet was frozen, and it wouldn't be the last. Our planet is struck by an ice age roughly every 100,000 years. Ice sheets and glaciers expand, reshaping the landscape, but normally stop before reaching the equator. 650 million years ago, that rule was broken. Most ice ages are triggered by changes in the planet's orbit around the sun. The further the Earth moves away from its star, the colder it gets. But factors like orbit and rotation aren't enough to explain ice stretching right down to the equator. That would have taken something far more dramatic. The smoking gun turned out to be our atmosphere, specifically greenhouse gases like carbon dioxide. Too much greenhouse gas causes global warming, but normal levels of CO2 provide the Earth with a moderate climate.
A greenhouse gas is any kind of gas which has the capacity to convert the sun's rays into heat. These gases are amazingly effective, making this planet the warm planet that it is today.
But it's a delicate balancing act. If levels of CO2 grow too high or too low, the climate will spiral into chaos. Too much, and the planet warms. Too little, and it cools.
Carbon dioxide is a very important gas. It's both our dilemma and our solution when it's there in too great a proportion that overheats the Earth, which of course we're worried about today. However, in the time leading up to Snowball Earth, we had the opposite problem. There wasn't enough carbon dioxide, and the Earth began to cool to a point where there was a runaway refrigeration that locked this Earth up in an icy crust.
Gehling believes that a drop in carbon dioxide levels caused the Snowball Earth disaster. Something was removing the CO2 on a huge scale. And there's only one process capable of doing that: weathering. It occurs when carbon dioxide mixes with water vapor to form acid rain. When acid rain falls on rocks, it reacts with minerals, locking the CO2 in the water that runs off. It then washes down to the sea, where it helps form solid limestone. Carbon dioxide that was once in the atmosphere is now locked in rock on the seafloor.
When weathering occurs at a great rate, you strip away rocks with acid rain, and that takes carbon dioxide out of the atmosphere and makes sure that it's locked away in the ocean.
Weathering happens more quickly in hot and humid locations. Normally, at least some of Earth's landmasses are too far north or south for weathering to be a major factor. But 650 million years ago, all the Earth's landmasses, from Death Valley to Australia, were clumped together into one big supercontinent at the equator, a hot, humid zone with the greatest rainfall on Earth. The weathering process went into overdrive. CO2 levels crashed, and so did the Earth's temperature.
You have carbon dioxide being taken out and not replaced, and as a result, the Earth inevitably has to cool.
Normally, the Earth's plants and animals balance the levels of carbon dioxide in the atmosphere, ensuring it's neither too hot nor too cold. But 650 million years ago, life on land was yet to evolve. In the oceans, life was still emerging as simple single-celled bacteria. In fact, the bacteria were actually making the situation worse.
650 million years ago, this is a world of cyanobacteria. Bacteria that formed a slime layer on the seafloor. Cyanobacteria are tiny organisms that have been around on this planet for 3 billion years before Snowball Earth. But at this time, they were particularly important.
These cyanobacteria sucked even more carbon dioxide from the oceans and locked it into limestone reefs called stromatolites. Some of this ancient carbon dioxide is still locked up in fossilized reefs, like these in southern Australia. When Jim Gayling pours a weak acid onto them, the ancient carbon dioxide that has been locked away for hundreds of millions of years is released.
What you'll see is an effervescence. Those white bubbles are carbon dioxide that had been locked up in these stromatolites, being released back into the atmosphere.
Rather than stabilizing the carbon dioxide levels, the cyanobacteria were depleting them further. In combination with weathering, they sucked the carbon dioxide out of the atmosphere, and temperatures dropped. "8:27 and 30 seconds in the evening on our clock of Earth history. Snowball Earth, 650 million years ago and counting. Ice was advancing from the poles. It happens during all ice ages. Normally it stops, but not this time. Instead, it just kept on marching towards the equator. As it did, it triggered a chain reaction that pushed the primitive life in the oceans to the edge of extinction. The Earth's surface is made up of land, open ocean, and ice. These surfaces all reflect sunlight differently, and that's the key to what happened next. Here in the Arctic, geophysicist Don Perovich heads for the boundary where the sea ice meets open water. It's a point scientists call the lead edge, and one of the best places to study how the Earth tipped over into the catastrophic deep freeze.
This is the place where the ice that's frozen to the shore meets the open Arctic Ocean. But it's more than that. The lead is where there's water, the lead's where there's light, and so the lead's where there's life. We see whales going by and seals and birds flying above. It's an incredibly productive area.
Here, Perovich can compare the reflectivity, or albedo, of two very different surfaces, the sea ice and open ocean. His sensor measures the amount of sunlight hitting the snow and the amount it reflects back. Sea ice is the most reflective surface on the planet. It reflects 85% of the sunlight that hits it.
If we were to just go out there, just 100 yards away to the lead, the albedo would be less than 10%. And what's interesting about this is this snow-covered ice has the largest albedo of any naturally occurring surface on Earth, and the open ocean has the smallest. So right here, we have a contrast between the best natural reflector and the worst natural reflector.
Open sea reflects very little light back into space. It absorbs the energy in the sunlight, keeping the planet warm. Scientists believe that 650 million years ago, the opposite happened. Earth's best reflector, sea ice, was replacing its worst reflector, sea water. When enough ice had formed, the remaining ocean couldn't absorb enough heat. So the Earth cooled. So more sea ice built up. That reflected more sunlight. The Earth got colder, and that made still more ice. It was the point of no return.
Let's say we grow a little bit more ice. So we're replacing the worst reflector with the best reflector. We'll cool things off, we'll get more ice, and we'll cool it off more, and it builds upon itself.
A runaway freezing effect capable of turning the whole planet into an ice ball. It's an idea no one even considered until a few decades ago. Scientists only discovered it was possible when they were studying another kind of disaster altogether. A nuclear war. During the Cold War, researchers predicted that a nuclear war could push enough smoke and dust into the atmosphere to block out the sun and initiate a global freeze. Russian climate modeler Mikhail Budiko was investigating this scenario when he made a chilling discovery. He calculated that if the ice sheet spread beyond 30 degrees latitude, as far south as New Orleans, they would reflect so much of the sun's energy that the Earth would reach an irreversible tipping point.
So when we have a system like the Earth with these feedbacks, one of the things that's talked about a lot is tipping points. You can think of it as you're in a boat rocking back and forth, not much changes until you go too far, and then you're in a new state. And Budiko's work said that if we moved the ice down far enough, we'd reach a tipping point and cover the whole Earth with it.
Budiko calculated that if the ice ever reached this tipping point, the planet would no longer absorb enough heat to keep the ice in check. The planet would be entombed in ice, from pole to pole. The theory is that 650 million years ago, this was exactly what happened. 8:28 p.m. on our clock representing the Earth's history. Deep beneath the ice sheets, single-celled organisms, the only life on the planet, faced a tough choice: adapt or die. Bacteria that had evolved over 3 billion years now faced extinction. But what would happen to life if Snowball Earth repeated itself today? Could we survive the same conditions? As ice sheets spread down from the poles, supplies of fresh water would freeze solid. Crops and livestock would perish worldwide. Industry would grind to a halt.
You could not run a nuclear power plant long enough to get through the snowball.
Many experts believe that humanity could find ways to live through a short-term ice age. But the odds of surviving a snowball Earth are next to nothing.
If humans ever experience a snowball Earth, we will quite bluntly be out of control. There is no way we could stop it. It would be easier to live on the surface of Mars, probably, than on the surface of Earth during a snowball.
The thick layer of ice covering the planet would become humanity's tombstone. 650 million years ago, the only life facing extinction was single-celled bacteria. Even their survival seemed improbable, but here we are. Life clearly did survive. The question is, how? The quest to learn how ancient organisms kept evolution alive has brought this lone microbiologist to Whiteout Glacier in southern Alaska. Here, Hazel Barton studies how life could survive a global deep freeze. Her mission is to find signs of life in some very dead-looking frozen caves.
People used to think that caves were devoid of life, that there was nothing in there. But it turns out they're actually teeming with microorganisms.
Barton searches for modern-day microbes living in this ice cave to learn how their ancient ancestors survived the mother of all climate disasters millions of years ago.
If you look on the edge of the cave, you can see all the particle dust that's got lodged in the ice. And it creates a surface that the microbes can actually live on.
This cave runs underneath the glacier. Inside, it's 4 degrees below freezing. Organisms that live in conditions this harsh are rightly called extremophiles. Barton takes samples of the microbes buried in freezing rock sediments at the base of the glacier. Barton believes this cave can shed light on how microbes adapted to conditions during Snowball Earth. The deeper Barton goes into the cave, the darker and colder it gets. But even here, life hangs on.
This is a community that looks like cyanobacteria. They're incredibly resistant to all kinds of stress that you would put them under. They can survive it.
During Snowball Earth, the ice was thousands of feet thick. Barton finds similar conditions hundreds of feet deeper into the cave. Here, there's hardly any light at all. But even in this dim, icy world, Barton finds microbes thriving.
So what we're looking at are microorganisms that have to adapt and generate energy when there is no sunlight. So what they do is they pull energy from the rock itself. They actually chew into the rock to get that energy.
Outside, Barton trains her field microscope on the samples she's collected. She believes the ancient microbes had similar structures to the cyanobacteria and were consummate survivors.
We're seeing cyanobacteria. There's a whole community living in that ice. Cyanobacteria really are these amazing organisms. They're very, very adaptive. They're one of the most ancient forms of life on our planet. They can survive some really extreme conditions.
Cyanobacteria have evolved amazing survival mechanisms. If our cells freeze, they burst their walls. If they dry out, they die. But cyanobacteria have evolved a cell structure that prevents rupturing in some of the most extreme conditions on Earth.
They've changed the structure of their DNA so it doesn't get damaged. If you were to take us and dry us, then, our DNA would be irreparable. You do that to a cyanobacteria, and you just have to add water 100 years later, and within a few hours, it's starting to carry out photosynthesis again.
Just as some could cope with dry conditions, others could cope with ice. As the ice rolled over them, most microbes died. But the hardiest survived. Over time, strains evolved that thrived in the cold and dark, to become the ancestors of every living thing on Earth today.
Everybody thinks about these global catastrophes like it's going to wipe out all life. And it's like, no, these microorganisms have been going through similar things for billions of years. And they're adaptive and they change. And then they fill the niche that's left behind.
Barton's research proves that even in the most extreme conditions, in the ice, in the dark, life finds a way.
Short of an object the size of Mars hitting the planet, you know, life will go on Earth. And events that we may think are, you know, catastrophic just simply turn over a new leaf and we start seeing a different form of life on Earth.
The only reason we are here today is because life adapted and survived. But for life to move on and evolve, the Earth had to melt. 8:35 p.m. on our clock of Earth's history. The planet's surface has been locked in ice for almost 25 million years. But then at 8:37 p.m., something remarkable happened. The ice sheets began to recede. Something was warming the Earth. But it wasn't the sun. The thing that would save the planet was actually inside the Earth itself, buried deep below the ice. This is Mount Augustine, Alaska, in the Aleutian Islands, one of the most volcanic regions on the planet. Mount Augustine has been active for over 40,000 years and is still erupting today. Volcanologist John Power heads there to learn how volcanoes could have saved us from the global deep freeze. Because volcanoes are the only things on the planet hot enough, strong enough, to thaw a frozen world.
We're on our way to Augustine Volcano. It's one of the most active volcanoes in the region. Last erupted in 2006. It all comes to play here at Augustine.
A fiery hell lies under Mount Augustine. During the last eruption in 2006, 17 billion tons of molten lava and ash exploded into the atmosphere. So much material spewed out in the blast, the volcano actually increased its own height.
We're about 100 feet higher than the summit of the volcano was prior to the eruption. This is some of the newest land in North America.
Using his field thermometer, John Power takes the temperature from just below the surface.
We've got a temperature of about 95, 96 degrees centigrade. So the summit of the volcano is still very hot. If you wanted to cook some potatoes, fry up some eggs, this would be exactly the spot to do it.
Mount Augustine is hot, but it's hard to believe that a volcano, even one this powerful, could punch through an ice sheet several thousand feet thick.
Where we are now has been covered with glacial ice as recently probably as 10, 15, 20,000 years ago. This was all underneath a glacier at that point in time.
When Power examined volcanic rocks here, he found evidence that 24,000 years ago, an eruption smashed its way up through the ice.
There is absolutely no problem for a volcano like Augustine or its neighbors to erupt through an ice sheet that could be either several kilometers or several miles thick.
We know it's possible because we've seen it happen. In 1996, the Grmsvtn volcano in Iceland erupted right through a glacier. It punched its way to the surface through more than half a mile of ice. The torrents of hot gases and ash blew a giant hole in the glacier. The heat of the eruption was so great it produced a giant melt, where 5 hours of flash floods carried 45,000 tons of water a second. But on a global scale, that's nothing. When the whole world was frozen, a few little holes wouldn't have made much difference. But volcanoes have another formidable weapon in their arsenal. They spew out more than just lava and rocks. Volcanoes also produce huge amounts of greenhouse gases.
Carbon dioxide is one of the very dominant species of gas that is coming out of volcanoes. There have been times when we've had certainly, thousands of tons per day coming out of this volcano.
Mount Augustine is dwarfed by the volcanoes that broke through the ice of Snowball Earth. Scientists believe that thousands of them ejected billions of tons of carbon dioxide into the atmosphere. Over a period of around 1 million years, this caused carbon dioxide levels to rise, reversing the depletion that created Snowball Earth and tipping the balance in the opposite direction.
Carbon dioxide rapidly built up in the atmosphere until it got to a critical point where we had a super meltdown of the ice, and that was the death knell of Snowball Earth.
The carbon dioxide-rich atmosphere trapped the sunlight, increased temperatures, and finally melted the ice. 635 million years ago, the Earth was saved from a global deep freeze by volcanoes. Volcanic eruptions released billions of tons of carbon dioxide into the atmosphere. The CO2 captured the heat of the sun, warming the world and melting the ice. After a 25 million year freeze, Snowball Earth was over. In the ocean, single-celled organisms had survived freezing conditions beneath the ice. But they were about to undergo the most extraordinary change, and fast. Roughly 3 million years after Snowball Earth ended, the new warm climate triggered an evolutionary explosion unlike any other. Single-celled bacteria evolved into multicelled creatures. The first ever complex organisms, and the ancestors of all animals, including us.
Snowball Earth must have been the closest thing to extinction of early life on Earth that we had. And yet we know creatures survived. And it can't be a coincidence that very soon after the waning stages of this Earth-wide ice age, we get the first large creatures. It really seems as though that series of environmental catastrophes spawned the kind of biology that could give rise to multicellularity.
Snowball Earth wasn't a catastrophe for life. In fact, it kick-started evolution. The key to this revolution was oxygen. Before the snowball, oxygen levels were only 1%, too little to support more complex organisms. After the deep freeze, levels rocketed to 21%. Scientists believe the boost in oxygen levels was the result of Ice Age chemistry. During Snowball Earth, the sun's ultraviolet rays reacted with water molecules in the ice to produce a chemical called hydrogen peroxide. This chemical remained locked in the frozen water until temperatures rose and the ice began to melt. The hydrogen peroxide broke down, releasing huge quantities of oxygen into the air and oceans. The quantum leap in oxygen levels now provided the fuel for life to evolve, from single to multi-celled organisms.
ages are really the bookmarks of evolution. It can be no coincidence that the evolution of animals was preceded by the largest ice age that the Earth has ever experienced.
The first multicellular organisms were the size of pinheads. These tiny embryonic creatures are the oldest multicellular fossils on the planet. The first links in the evolutionary chain that eventually leads to higher animals and humans. Over millions of years in the new oxygen-rich atmosphere, these creatures became more and more complex. In Australia, Jim Gayling studies the fossil remains of the creatures that inherited the planet after Snowball Earth.
After Snowball Earth, we see a revolution in the history of life from the fossil record, because for the first time, we see large creatures, creatures that anyone can see with the naked eye. They are the first animals on Earth.
This primitive sea creature is one of the first complex multicellular organisms. It lived and died around 50 million years after the end of Snowball Earth.
It's absolutely complete. You can see the gut, you can see the head end where the segments wrapped around it, and these incredibly fine segments just wrapped over the sea floor.
All the animals on the planet, including us, are descended from creatures like this.
You're looking at the first life forms which had patterns of cells and body plans that were the same as ours. Head, a tail, a belly, a back. Even though they're not necessarily our direct ancestors, these are the first creatures that represent the line of biology that gave rise to us.
All over the planet, similar organisms were evolving, making the leap from primitive to complex life.
There'd been life on this planet for more than 3 billion years. And it was really only the Snowball event that kick-started complex life. If it hadn't been for this ice age, this would have been slime world forever, and we wouldn't be sitting here talking about it. So if you want to put your finger on one point in the history of life that made a big difference, that was Snowball Earth.
From slime to all life on Earth in all of its frantic, colorful glory. Every living thing on the planet is likely the direct result of a catastrophic deep freeze that threatened to destroy life on Earth, but ended up creating life as we know it. We owe our existence to the greatest climate disaster the planet has ever known. Without Snowball Earth, we would not be here.